Okay, looks like the numbers of session now, so let's get started. Hello, everyone. Welcome to this COMET webinar, and thanks very much for joining us today. Just a quick note on logistics before we begin. The talk will be about 45 minutes, followed by around 10 minutes for Q&A. Please drop your questions into the Q&A box, and we'll pass them along to the speaker at the end. Today, we are very pleased to have our own Professor John Elliott as the speaker. John is Professor of Earth Observation and Active Tectonics at the University of Leeds and a Royal Society University Research Fellow. His research focuses on using Earth observation satellite data to understand deformation of the Earth's crust. More broadly, his interests lie in understanding how mountains grow and the seismic hazard associated with the active fault structures. So without further ado, I'll hand over to John.
Brilliant. Thank you, Jen. So if you just grab the lights. Thank you for the introduction. So yes, this afternoon I'll be talking about the deformation, strains and velocities across the Alpine Himalayan Belt. As a way of introduction, I'll introduce you to the large project that this is part of, the looking inside the continents from space, and the motivation for why we want to do these kinds of measurements. I'll also delve into what those measurements are, measuring surface strain rates before looking at previously published velocity fields, both from others and ourselves. Then I'll spend the bulk of the time on generating the velocity field, how we did that from combining GNSS and InSAR, and the time series analysis we do to be able to get those velocities as outputs and the strain rates that we ultimately want. I'll then end, hopefully we've got time to look at some of the tectonic regions that many of you have focused on and have been part of this work and other publications, before quickly looking at the vertical deformation signals, what we can and can't believe with those, and then ending on the future directions for satellite observations in this field. So this is really a summary of the work. There's been a big, huge team effort by many of the people here, and it's at some other universities as they've moved on. That's culminated in this European Space Agency special publication in the remote sensing environments, the deformation strains and velocities for the AHB, the Alpine Himalayan Belt. It's been a huge group effort. I've been fortunate to work with many great individuals here, and that's all been part of the Looking Inside the Continents from Space project. The ND was started by Tim and Barry Parsons in Oxford and other researchers, Phil, Greg and James here, where we were trying to look into the insights of earthquake hazard and crustal deformation, a large grant project that started, in fact, many years ago, well over a decade ago, so long ago that the research funder for it, NERC, the UK funder for this, Natural Environment Research Council, has gone through 3 logo iterations in the time it's taken us to finish this work. So really quite a long time. And it's involved many different investigators over the years, postdoctoral researchers and fellows, PhD students and various software engineers and technicians as well. That have all worked together to be able to build the system that's enabled this to happen. And there's been even more PhD students working on other aspects of velocity field generation too. So really a huge effort to be able to do this. Now, the LIX project was looking for scientific insight into the growth of mountains, the deformation of the continents, looking at what we see in the geomorphology, how has it got there, the tectonics of how that's different on the continents, through trying to understand the kinematics, the rates at which the plates are deforming, ultimately the fault rates, slip rates, things like that, to try and get at some of the underlying dynamics of the forces that are involved in generating these. And just these kinematic parts we're doing, the project I'm presenting here, was only 2 of the sort of 6 aspects that LIX were trying to address, 2 of the bits, the kinematics that we could get from the satellite geodesy. But also there's a societal motivation for doing this. This continental collision zone, where a lot of people live in large urban centres, has been the locus of many devastating earthquakes over the last 100 years. These fault lines rupture often near cities that are grown along these huge sort of topographic divides and fault lines. So there's a societal reason to better understand the distribution of seismic hazard as well. So the sort of context we've got, the geological context, the tectonics, we've got Eurasia here as your backstop, so that's your rigid backstop, against which the relative motion of the Nubia plate, the Eurobia plate and the Indian plate at different velocities from 5 to 40 to 50 millimeters per year northwards has given you this asymmetric convergence zone of continental collision with large amounts of deformation to north, 2-dimensional, not linear features, but 2-dimensional faulting that's pervasive throughout the Eurasian continent there due to the propagation of these plates and the ongoing deformation over many tens of millions of years that have led to this. So we do this to understand how we can link those rates we see today to the long-term tectonics we see. So the growth of these mountains, the growth of structures, folds and faulting. We want to look at the time varying behaviour of the earthquake cycle. These earthquakes, the co-seismic period, the post-seismic after. What we're trying to measure is the interseismic rates that lead up to these big earthquakes. And we're doing this at a big scale, a continental scale now, a transnational scale, trying to look at that distribution across the whole continent. Hopefully so that we can infer something about the nature of faulting at depth. And then hopefully to be able to link that build-up of strain to the release of earthquakes, the potency of those earthquakes, and to be able to bring that down to low straining areas if we can. What's the limit of what we can do with these observations? So as I was alluding to, hopefully this correlation that we see with where seismic moment is released, the energy in earthquakes here in both eastern Turkey and California, where that energy is released or how often those earthquakes occur, seems to map spatially, correlates very well with where the strain is building up, the strain rate. So areas here, say, that are relatively rigid, aseismic blue areas, they're not straining much, you don't get any earthquakes there. Those that are red hot, where you're straining very fast, building up that strain quickly, is where you tend to get more earthquakes, more often larger, it scales like that. So that's where the energy ultimately has to be released. So if we can better map the distribution of strain through space and then through time, then we might be better informed where the hazard lies. So if we give an example of measuring that strain, we need to be able to measure the gradients of velocity. To do that, we'll take the Tibetan Plateau here, a case study for many of the work we've done. We're looking at the Kunlun Fault here in the northeast, and a satellite image across this area. We've got north, up, east to the right, and it's about 100-kilometre width here. So that's the fault running through the mountains here, the Kunlun Fault. It's had large earthquakes in the past. If we take a geophysical approach and draw a nice straight line through it, ignoring how bendy it is just for simplicity, and look at the velocities across it. Now, with strains, you can measure things relatively. So if we say in the south, the eastward velocity is 0 everywhere. In the north, the eastward velocity is 10 millimeters per year. And then to keep it simple, the northward velocity is 0 everywhere. Now that's relative. There is some northward motion, but if we say relative across the fault, it's north 0 everywhere, just for simplicity here. Now this kind of motion is synonymous with a right lateral fault, strain accumulation across that. And if we imagine building a large fence around a square field at 100-kilometre scale, in the course of a year, it would be offset by 10 millimeters per year. That's the simple shear that you'd get across this area. Now, it's not exactly linear in real life. It does have a different shape, but just for simplicity, let's imagine that. Now, we want to understand the velocity gradients in different directions. So how the northward velocity changes as you move north is 0, because there's no northward velocity. Similarly, it doesn't change in east direction. It's just 0 everywhere. So those two components are 0. How does the eastward velocity change as you move eastwards? Well, in the south, it's constant, and in the north, it's constant. So it's not varying. So that's 0. So the only thing that's varying in this simple setup is the eastward velocity as you move northwards is going from 0 to 10. So that's 10 to the minus 2 meters per year over a distance of 10 to the 5 meters. That gives you a strain rate of 10 to the minus 7 per year, or 3 times 10 to the minus 15 seconds. So that's 100 nanostrains. So when I show you the figures later, that's quite fast. 100 nanostrains, ballpark roughly, is associated with this kind of slipping. So if we go to that horizontal velocity gradient tensor, we put those 4 gradients in it. That's what we get. That's the horizontal velocity gradient tensor. And from that, we want to get at strain. Now, the strain comes from that velocity gradient tensor. It can be split into 2 parts. It's a summation of a symmetric part, the strain rate tensor, and an anti-symmetric, the rotation rate, W here. So that can be done with a simple trick of taking the transpose of that velocity gradient tensor and adding it to get the symmetric part, or subtracting it to get the anti-symmetric part. So again, if we present that again, a velocity gradient and our definition of strain rate tensor, for our simple example here, the 4 components, when we do that, this is the equation we get for it. So for our toy example that we presented before, it has a diagonal of zeros, and then our off diagonals are half 10 to the minus 7. That then is our strain rate tensor. So those are the things we want. Now, rather than presenting it as that tensor, the maps that I'll show you later on tend to give a nice picture of a magnitude. And we call that the second invariant, even though it strictly isn't. It's a norm in the matrix. But The second invariant gives you the overall magnitude of the strain, and that's how you get it from the sum of the squares of those components. And it's a good way of giving you a colour scale map. We can also look at the maximum shear strain rate, but that's strongly related to that second invariant when there's no dilatation. It's just a factor or two different, and that gives you the peak shearing deformation. So that kind of measure we want, particularly with strike slip faults. It's very good for looking at that. Then we can get the dilatation rate, and that comes from the sum of the trace of those components. That's the first invariant, and that tells you whether an area is getting bigger or whether it's getting smaller, contraction. So that's a useful measure in areas of convergence or extension. And then finally, we've got that rotation rate tensor, the antisymmetric bit, where we look at the vorticity vector, which is just twice that rotation tensor. And then there's also an extra thing we had to do when working at this scale, which was to correct for the Earth being a sphere, the spherical correction. So you take into account the co-latitude that you're working at. So there's an extra correction term for 3 of those components to take into account that, which makes a long wavelength impact as well. That's just an extra detail that's in the paper. So previous strain rate maps have done this at a global scale with GNSS. Corny Kramer has done that with a global strain rate map that gave us this beautiful picture at a huge scale of the kinematics building up. This was just over a decade ago, this version. And then more recently, at the end of last year, Nicola presented their compilation of GNSS for the Alpine Himalayan Belt, providing the strain rate for that area as well. And in fact, he gave a COMET webinar a couple of years ago, and I highly recommend viewing that one for some more details on their publications in this area. So the difference we're now making is those previous studies had GNSS. So what LIX tried to do was introduce the extra information that could be gained from satellite radar, in particular from the anticipated launch of Sentinel-1 in 2014 that would give us radar data over the continents to be able to measure surface velocities at a much higher resolution than the existing GNSS data. And this is a constellation of at least two satellites in orbit over that 10-year period, sun-synchronous orbits that give a revisit period of 12 days for an individual satellite, up to 6 days for the pair. And it acquires in an interferometric wide swath mode. That gives us 250 kilometres, much wider area coverage than was previously available with ERS and MSAT, say. So you could actually look at these continental scales when you were combining this. You could look at whole countries in just one take, and then combining these together, you can look over larger areas. Now, an important aspect of the ESA Copernicus data is its open access. So these large volumes of data are openly available to anyone who's able to process the large, big data sets. And that made a big difference to the scale at which you could operate at, which you couldn't do before when you could only look at individual faults. So this was done with the first 5 years of data with Jonathan Weiss's work on Turkey, which was able to do complete coverage of Anatolian, North Anatolian Fault and East Anatolian Fault as well, using about, what was it? It was about 30,000 interferograms to generate this from those 5 years of data. And that was able to give coverage of about just under 1 million square kilometres, so one's country, and was able to show the overall kinematics of the area in agreement, large strain gradients, velocity gradients across the North Anatolian Fault and a relatively rigid Eastern Anatolia. Then Andrew Watson with his PhD was able to scale that up then by over a factor of 2 to over 2 million square kilometres to do the whole of Iran, in which he was able to measure really quite diffuse deformation across most of Iran that's deforming with concentrated zone across some of the strike slip faults, broadly diffuse across the Zagros, and really quite a wealth of really short wavelength deformation, not related to tectonics, but due to groundwater extraction, salt diapirism, and sediment motion. But he was able to really scale that up to a much bigger distance and using more recent data. And then finally, just recently published, even twice the size now, 4 million square kilometres, was the Tibetan velocity field just released, in which you see a sort of mixed mode of really quite focused strain on some of the really major strike slip faults, say of the Kunlun Fault where the Kokazili earthquake happened, and then a bit more distributed deformation across. So it's a mixed mode behaviour of blocks and faulting that was found here, but read that study for the latest findings on that. So for this talk, I'm going to focus on the big scale of the Alpine Himalayan Belt and how we went about generating that velocity field with the combined SAR and GNSS. Now we took the methodology. I'll walk you through the various steps of doing this. We took all the Sentinel-1 radar images and then did a time series approach and a lot of corrections on that data to improve removing some of the atmospheric noise. And we needed to combine that with GNSS to give us a reference frame to be able to do it. and then through generate a sort of velocity field from that, strain rate outputs, and the three components of velocity, so that they're all open data. So I'll go through each of these steps in detail about how we achieve this. Starting with the GNSS compilation. Now, this was done by Chris Rollins, who did a huge effort in compiling over 70,000 velocities across the AHB from 171 studies. So this is the full list of papers, and it shows you the importance of the openness of data, people publishing their velocities and high quality metadata to be able to interrogate and then use this data and make it all consistent. And it involved many tens of thousands of mainly horizontal, but also three-dimensional velocities, and also some leveling rates as well. And he applied a number of correction steps to this to be able to get them all in a sort of consistent reference frame. So if I go through these very briefly, each of the data sets is tied into the ITRF reference frame. He compares GPS that look like they're collated, but the precision of their locations is not good enough to find out, and grouping them to see if they're the same station. He gets rid of outliers that may be too large, or their uncertainties are too fast, the velocities are too fast, or they're in areas of extreme subsidence. And he iterates on these anomalous velocities by comparing them to nearby sites to see if they're too different. He then aligns all the data sets with the common velocities many times, an iterative process, going through all the studies to make sure they all then match. He then reruns the outliers to get rid of any of the big differences, and then filters out velocities that have been more recently updated with longer time series or in newer compilations, before then combining any velocities that are too close together, averaging them out so that we don't get large strain rates over short distances. So if you just look at that then visually, this is the starting data set. There are some wildly extreme velocities that are out there. So you get rid of the huge outliers, you clean it up, you then look for small differences between them, and it thins out the data even more. And you do all those steps to make a sort of more consistent velocity field that doesn't have extreme differences in velocities over short wavelengths. So if we look at this then, the final velocities that are really quite a small percentage of those initial 70,000. This is in the ITRF reference frame, no net rotation reference frame. So a slightly different view of that with the magnitude of up to 60 millimeters per year. The more sort of usual perspective with respect to Eurasia, a fixed Eurasia, you can see that northward motion of India and Arabia, and the westward motion of Anatolia out of the way. That's the more usual picture we see for the GNSS. So you can see it's really quite heterogeneous in its distribution, dense in Europe, but really huge gaps in the middle of Afghanistan, and really quite sparse in parts of Central Asia as well, and very little across the central part of the Tibetan Plateau. So if we look at that then more easily, you can see that in Italy up to 100 sites per square kilometre, but areas where you've got only one station per square kilometre. So that's where we're envisaging the InSAR can add value. It's not in Europe, where all of this is really very well constrained by GNSS, which is a more precise measure of surface velocities. It's to fill in the gaps where there is relatively sparse deformation out there. As I said, there was also leveling measurements, but these are largely constrained to China, but they give quite important constraints then on the vertical rates here. You can see the large subsidence rate that I'll end on around Beijing. So this is all available on Chris's GitHub. It's an excellent compilation of rigorously combined velocities together. They're all consistent. It's been released with this paper, but he has done a couple of updates and will probably continue to add new studies in. So it's a wealth of important information for those that even may just want to use the GNSS data itself. But as I said, what we're trying to do with the InSAR is fill in some of those gaps in terms of the resolution. Could we get a bit more information on those surface velocities and gradients? And I'll lead you through how we did that now. So as I said, we combined the Sentinel-1 SAR data on both the ascending and descending for about 460 frames on each, using the sort of LIXAR processing system at the Jasmine High Performance Computing Facility. And each frame is what we've defined to be about 30 bursts long. So it gives us coverage over this sort of 11,000 kilometers in both look directions that are available. So these all serve through the LIXAR portal here, and we generate those interferograms about 100 meter resolution. They could be high resolution, but the data volumes are quite large. But that's our sort of starting data, the interferograms that we get. And we've produced many of those on the ascending and descending direction for the last sort of decade. And what we do is we build networks of interferograms, this time baseline time plot, We have generated over 1 million interferograms for this study, a huge number of interferograms. This is an example across Iran to be able to make these observations. Now, unfortunately, it's not usually as coherent as this. What I mean is the data coverage is not always this complete. This is an example from the Eastern Syntaxis in the Himalayas, Eastern Himalayas, where we've actually got no data recovery. This is low coherence. And what I mean by coherence, interferometric coherence, is a measure here from bright to dark, 1 to 0, of the similarity of two SAR images that enables us to do the interferometry. It's the stability of the scatterers that you get from the radar change. So high areas that are good are urban areas, rock outcrop areas, bare earth areas that we can get a good signal from. Poor areas are areas of vegetation here in the north, or the Caspian Sea water where you can't get any coherence over the time period, where we can't retrieve any data. So we're looking for coherent areas to do this. So it's a challenge in vegetated areas to maintain this. This can be seen at the Alpine Himalayan scale. In Europe, it's sort of mixed. Spain is relatively dry, so you get relatively good coherence. In Iran, you get brilliant coherence for the most part when you've not got shifting sand, but you've got stable desert. And then across various parts of Central Asia, it's mixed. Some of the plateaus are very good, like coloured ones, but various parts that are highly vegetated in Southeast Asia really have low coherence. So it's really a challenge with C-band Sentinel-1 data to be able to do any observations. So it's very hard to go further east. So after generating all these interferograms, there's a lot of noise in them because we're trying to measure small velocities, small strain rates, and a large amount of that noise comes from the atmosphere, in particular the tropospheric water vapor and the hydrostatic delay that you get with it, and the ionosphere contributions. So we make a couple of corrections to those when we do the unwrapping. Plus, we also do one for the solid earth tide that I'll go into as well. So the atmospheric corrections for the troposphere are done through GACOS. So Chen Yu and Chenghon Lee have built this generic atmospheric correction online service for InSAR. So GACOS, you can go and download these corrections for this. So it's a huge important part of the LIXAR process to be able to try and beat down some of the noise. So if I show you an example from Andrew's work over Iran, on the left, we've got without the GACOS correction for a few frames. Then with the GACOS correction, the impact that has on the data, and then the difference, what GACOS is changing in those velocities. Now, at the long wavelength, it's affecting the pressure fields, the hydrostatic atmospheric phase screen, and at short wavelengths, it's capturing a bit of the turbulent, but mainly the sort of height-dependent correction that we get here. So it generally, in most areas, reduces some of the noise most of the time. Some areas, particularly near coasts, it doesn't do so well, or ocean islands. But in other areas, it does improve. But it does need checking as to what it's doing. So at a large scale, then again, across the whole Alpine Himalayan Belt, this is the sort of level of corrections that GACOS is doing in the time series. So about plus or minus 5 millimeters per year is doing to each of the frames, but mostly less than that, averaged over the whole time. Then we've got the solid earth tide. So this is due to the sun-moon interaction on the Earth. And we use the Earth Tide tool in GMT to correct for this. Now, this is a lot smaller. It's way less than 1 most of the time, this correction that we need to make. It's the solid earth tide, not the ocean tide, that we need to do over the long term here, but it's a relatively small correction for that. So if we look at this slightly differently now, for on the left descending frames and on the right ascending frames, for the top troposphere corrections and bottom solid earth tide corrections, we can see the sort of scale of these in terms of the mean gradient, how big that correction is in millimeters per kilometer across the whole scene. So for the troposphere is a lot bigger, and it's coloured by latitude. It's a lot bigger at lower latitudes for the troposphere and then at higher latitudes, and it's a bit bigger for the ascending frames than for the descending frames. And then the solid earth tide is a lot smaller. In order to magnitude, note the difference in the scale. It's a lot smaller, those gradients. Then we move on to corrections for the ionosphere. So that causes also an impact on the propagation of the radar. This is due to the total electron content around about 450 kilometers, but it's spread in different layers, but largely beneath the satellite at 700 kilometers. And these are the sort of size of corrections that we need on ascending and descending. So there's quite a marked difference due to the time of day. So in the late afternoon, evening for the ascending, the early morning, descending, the activity of the ionosphere is very different. So the corrections are a very different order of magnitude for those. But we also correct for that as well. So we look at that, then this is due to the impact of the 11-year solar cycle, the sunspot cycle. So if we look at this through time of Sentinel-1 from about end of 2014 through to 2024, this was actually almost the full cycle of the sun from its minimum in 2019 to its maximum in 2024. So that's the sunspot number that we see in the background here. So for descending, it's very small, but it's increasing through time, through later in the time series. And on the ascending, you see it's much larger. And again, increasing in time and increasing to lower latitudes as well. That's the sort of big scale that we're seeing with this. So once we've done those corrections to the interferograms, we can move then on to the time series analysis that gives us the velocities that we want and displacement histories. So this is entirely dependent on the work from Yu Morishita in generating the LIXPAS time series analysis algorithm that's available on GitHub, previously published, that ingests those interferograms and Gauss corrections to be able to build a sort of system of checks and quality assurances for getting good interferograms that then go into the time series inversion to estimate the displacement history and the long-term velocity and measures of uncertainty and some quality metrics as well that we can look at. So what we do is we get the interferograms at about 100 meters. We check the loops of them to see if there's been good phase unwrapping, throwing out those with unwrapping errors, and then doing some filtering at the end, spatial temporal filtering to try and reduce some of the remaining noise that Gauss hasn't corrected for, and get those average velocities and standard deviations and the displacement time history. So that's the time series bit through LIXPAS. So if we look at a particular individual frame across the Alpine fault from Droit, this is the velocity that we get out, the average velocity as a map relative to reference pixel. And then if we take a point in the middle and look at its time series, its history of displacement, you can see in red the unfiltered time series, the displacements we get through time. And then the filter, the spatial temporal filter, then tightens this up a bit, removing some of that noise. And you can see the sort of sinusoidal annual seasonal signals that we're getting there. But we're getting quite a good measure then at a long-term rate. So here, 4 millimeters per year relative to the reference pixel. And then there's some measure of uncertainty that can go with that. So the quality metrics that LIXPAS is doing is trying to get us to have a mask here that we can remove some of the velocities that we don't believe. And that's based on things like the coherence, how many unwrapped interferograms, the length of time over which we're looking at the interferograms, any gaps in the time series that cause problems with estimating velocity, number of loop errors, lots of different metrics that can be thresholded to be able to remove some of the pixels. And for the HB work, we actually adapted that by region. So there's a metadata spreadsheet of what different values we took for these through it. So one of those is a measure of uncertainty that you get at the end, the uncertainty in the velocity from the bootstrapping of all those. It's only a formal uncertainty. And one of the drawbacks of it is it has a reference pixel problem in that it's 0 near the reference pixel. So we rescale all of these back up so we get slightly more realistic, by looking at spatial variogram here, more realistic estimates of those near the reference point. But they're still underestimates of the true uncertainty, and I'll come back to that later. They're just an estimate of our uncertainty in the velocity. There's another thing that is a concern when looking at these interferograms, and that's a sort of phase bias. Looking at something that's probably related to do with the soil moisture, the impact of multi-looking on distributed scatterers that we get, particularly when we've got short period interferograms. And we try and have some measure this from the loop closure failure for the networks that we do, trying to look at where it's worse. So in RAM, we think it's less bad, less vegetation, less moisture, and other areas where we think it's more of a problem. We partially tried to mitigate this by actually producing a lot of long period interferograms, but we haven't done that systematically everywhere. And EASA has a sort of a correction method for being able to prove this. So in future, we hope to be able to actually more directly correct for this, but it's still an issue in some of the results. Additionally, we have to account for earthquakes in our time series. So these earthquakes cause co-seismic steps that would look like really high strain. Now, they obviously are high strain release, but they're not the bit we want to measure. We want to get rid of those. So we truncate our time series or solve for a co-seismic offset for these magnitude 6+ earthquakes that have happened in the air. The thing we don't do, different from the GNSS community, is we've not corrected for the post-seismic, and you see that later in all the strain rates. The post-seismic we do not remove or account for at this stage. And then one other correction we have to do is for the plate motion. So this is to account for the fact that the plates are moving relative to the orbital reference frame, the Earth-centered reference frame. So in this case, they're moving all eastward relative to the orbit. So over 10 years, it's moving quite a lot to where the orbital ephemeris data is saying it is. This gives a long wavelength ramp that needs to be corrected for, near linear, but it's got a bit of a shape to it. So across large tracts here, this needs to be removed from all of the data sets as well. So if we look again at the Alpine Himalayan scale, this is the kind of magnitude of correction that needs to be made to be able to sort of correct those line of sight so they're more consistent for that. So if we look at that combined together, here's an example of a frame in Iran. Before we apply those corrections, this is the velocity you'd get. The magnitude of each of those corrections on the same color scale. So the solid earth tide not doing much, the ionosphere long wavelength large, plate motion long wavelength small, troposphere bit of a long wavelength, but also short wavelength corrections. So the final velocity here is a more flattened interferogram with slightly reduced noise. And then in the time series, each individual epoch then is much improved relative to the uncorrected one. You get a much smoother, more consistent long-term rate, with still a lot of scatter, but it's better than not doing it at all. So then this is the result we get. These are the line of sight velocities on ascending and descending across the whole air. They look pretty nice meshed together. You can start to see some of the velocity gradients in here, but InSAR is always relative. They're not tied together. They've been corrected best we can, reducing the noise, but they're not all referenced together. These are all just locally referenced to each other, zeroed. So they don't give you the cumulative velocity across a large area. We also have those uncertainties, as I said, that were a little bit low. So these are the uncertainties we get from the bootstrapping approach to the time series that we flatten to account for the reference pixel. But these are all largely below 1, except where we've had a bit of problems with some of the frames. But they're too low, and we'll get back to adjusting them. So the next stage is to look at how we generate then the velocity field. So we want that to then go onto the strains. So this is done through a piece of software called Velma that Hua Wang developed. And is used in many studies before, Wang et al., used across large parts of the Tibetan Plateau. And this is key for being able to tie together the InSAR data that I just showed you with the earlier GNSS data to give you a consistent velocity frame. So we get the GNSS, we combine that with the two line of sight velocities from ascending and descending of the SAR, and we did that over a mesh. We had quite a coarse node spacing of 40 kilometers so that we solved the velocities on that triangular mesh. How fast are each of them going? And that's to enable us to reference all the line of sight velocity frames. So we've got to adjust all of them. We've got to adjust them for any remaining long wavelength impact that we haven't accounted for. This is usually quadratic or planar. And also doing a linear atmospheric correction with height for any sort of troposphere that we're missing too from any of the earlier corrections. So it's just an adjustment to make them all consistent with each other. And it's done over a very large area in one big mesh. So these are line of sight velocities not referenced to each other, not through VelMap and the GNSS. This is then referenced. So you can see the impact that has. And all the velocities then are consistent apart from the slight divergence of line of sight across the frame, but they give you that overall, say, east-west motion that contribute largely towards the ascending and descending. So we take the northward component from the GNSS because the InSAR only gives us 2 components and it's mainly sensitive to east-west and vertical. It's not sensitive to north, so we have to use the GNSS velocity field to generate a long wavelength smooth northward. So we combine that with the ascending and descending on a pixel by pixel basis to do a decomposition at the 1 kilometer resolution of our time series to give an eastward component and a vertical component. So north from GNSS, east and vertical from the combination of the SAR and the GNSS. So if we look at those individually now, the northward component just from the GNSS, taking a profile from India all the way through the collision zone out past Tian Shan, north to south. This is the profile you get through there. Really quite smooth, obviously fits the GNSS well because that's what's constraining it, but you get the overall convergence 40 millimeters per year across this region. If we then look at the eastward component on a really quite long, small circle arc from Greece all the way through Anatolia, the Tibetan Plateau to the Sichuan Basin, that shows really quite a nice long wavelength signal that's really captured at this scale. It fits the GNSS well because, of course, that's partly constrained by it. And you can see the sort of scatter anywhere is about plus or minus 10 millimeters per year, but we've really got a consistent signal over that huge length scale. And it's really over 8,000 kilometers, a good fraction of the Earth around there. And then finally, the vertical, and I'll come back to it a bit later, how much we can believe this, but if we do a vertical profile from the Zagros through the Western Tibetan Plateau to the Ordos, this is the profile that we see in that. And you can see in this, it's centered around 0. It's very noisy, and it's hard to be confident of any long wavelength signals that we're seeing. And that needs to be worked on in future, whether we can get something useful out of that. As I said, the uncertainties, the formal uncertainties from the time series approach, because the time series are getting longer and longer and lots of dates, the bootstrap tends to underestimate the true uncertainty. So we can actually use the redundancy of the look directions from the InSAR, because in many areas we've got 4 different look directions. So we can estimate the velocities using 3 and compare it to an independent 4th direction we didn't use, and try and calculate what that line of sight should have been and compare it to that. So we've got a check on it, what it should have been from our velocity field. And when we do that, the RMS for that really goes up. It's about more than twice, probably. You're talking more like 2.5 millimeters per year for the misfit for these reconstructed line of sights on the overlap regions. So that's a bit better. So if we compare our GNSS east velocity with our InSAR, we obviously get a good match because they're not independent. We've constrained it to that. But this is the kind of misfit that we still get. It's at the 2.5 millimeters per year. Leveling is a bit better, but the GNSS is a bit worse. So that's the kind of noise. And then in the vertical, it's still really quite large. These are not things we can use in the vertical. Similarly, if we compare the European Ground Motion Service, this is our result in the east component. This is European Ground Motion Service that for quite many years has been producing an incredibly dense, high-resolution velocity field for Europe on a regular basis. It looks patchy, but it's actually very dense. That's why it looks patchy. They've got lots of data there. We can compare what they get against the GNSS. So they get an incredibly tight fit. They do a very good job at the velocities in Europe. It's very hard on the vertical, but in Europe, it's a millimeter per year, their products. Whereas for us in Europe, we're just as noisy as anywhere, it's 2.5 millimeters per year. So Europe, we're not adding any information. It's well constrained with GNSS. EGMS does great InSAR over that area. There's not much going on in large parts of it. Where we're adding value is where there's no GNSS, other parts of the world where there's lots of deformation is where it's important. So if we then move to those strain rates, calculating what we want, this is the filtered velocities we start with. We can't work with really high resolution velocities because there's a lot of short wavelength noise in it. So it has a 150 kilometer medium filter to smooth out some of that short wavelength effect to be able to get those calculations. Now use those equations that I showed you before, the gradients in the east velocities, for instance, they go into that, we can calculate the strain rate. This is our sort of answer for the magnitude of where it's accumulating strain. So North Anatolian Fault, huge amount of strain along that. Large faults in the Tibetan Plateau, the Janjuru Fault, the Kunlun Fault, the Altin-Tag in particular fault shows high concentrations along with the Himalayan shortening region. And the Pamirs really pops out here, huge amounts of strain across that. Similarly, if we look at the shear, maximum shear component, it sort of cleans it up for the strike-slip faults. They're the ones that are undergoing that shear. So you really see the locus of that. But there are just huge swathes of areas that really are very low strain rates, below 20 nanostrain per year, so really quite low. But there are regions such as the Tian Shan where really quite broad, low, measurable, but really quite broad distributed deformation. And of course the Tibetan Plateau as well. But there are relatively rigid aseismic areas. And then of course Europe really is quite low rates for large parts of it, other than the bits of Greece and the Corinth area that are very huge strain. So if we compare this to what that InSAR is adding, as I said, in Europe, it's not really adding much. This is the maximum shear you get with just the GNSS data, if you just calculate it using that. So you get the big picture, you get where it's 0, but in areas, you don't get the detail. So when we add in the InSAR, you can see it really tightens it up in the areas. It really shows you the strain is localized on some of these big fault structures. And it's very spread out when you've only got GNSS. But it definitely zones in. So the high resolution is adding information outside of Europe where there's not much GNSS, and the resolution of the SAR is adding something. So you can see that around these faults in the Tibetan Plateau, the Pamirs in particular, and along the North Anatolian Fault in Turkey. We can also compare it to the previous global strain rate model from before. So this is the GSRM done on the same color scale as ours. So again, it's got the broad scale picture, but it's really quite patchy in areas, and there's large strain concentrations where the GNSS probably were slightly contradictory. So Chris did a lot of cleaning of this. So we get a lot smoother, less high spurious peaks of strain and much more localized. So that's the improvement we've got from adding in the SAR. Also, you can't do anything with the offshore. Similarly, we can look at the dilatation, looking at the area changes here. So whether places are under compression, such as the Himalayas in purple, or Western Anatolia undergoing extension area increase, and the Greece Corinth region, and across the Tibetan Plateau, you can sort of make out the hints of that sort of change in the area there. So we've got the Pamirs, a lot of contraction, a lot of compression. The Tian Shan, very purple, so negative dilatation, showing that shortening, and the Caucasus as well. And then we can look at the vorticity. So this is then related to those strike-slip faults. They have that rotation component to them. So they get really picked out with that vorticity value. All along the Shaman fault, showing that, you know, India bashing into Eurasia, giving you that quite huge rotation there. But it's accommodated by the Shaman faults and those strike-slips. Dead Sea fault pops up, East Anatolian fault. And then Anatolia, you can see the counterclockwise rotation of that. Well, and then Greece is clockwise rotation. So they help sort of understand it a bit as well. So those data sets, those velocities, those strain rates are something that we've made openly available. So there's an online viewer to be able to see all that data overlaid with like the GNSS and faults. We've also put, along with the paper, the Synodo data repository with all those different outputs. So that's the 3 components of velocities, line of sight, reference velocities, the strain rates. They're all packaged up here, 1 kilometre resolution. And then because it was very large, the time series has been put on the CEDAR archive. So if you want for each of the frames, for each of the pixels, it's 10-year time history as well. Then there's this large data set that should be soon available to download as well. So you can look at all that. It's just pending review and release for now. So just to end then on the individual tectonics of different areas, I just want to focus on these to highlight some of the other studies that are done by the people, so you can refer to their papers. But we've got the creeping faults. Now, one of the things that we want to do looking at this sort of scale is to see how common this phenomena. So it's previously recognized that parts of the North Anatolian Fault, the Shaman fault zone, the Haiyuan and Shanchuhe fault creeped. Now, this is a seismic slip of faults, and if it's at the near surface, it provides quite a strong velocity gradient that gives you a large strain rate that should be really pop out on these strain rate maps. So we see these previously recognized areas as these spikes in the strain rate from these velocity contrasts. So they're there, but what we found is they're not prevalent. They're sort of exceptions, not rules. Looking across the whole Alpine Himalayan Belt, the ones that have already been found, have already been documented. It's not a common extensive feature of strike-slip faulting. Most of them are largely locked or straining and don't have pervasive near-surface creep. You can also then, if you look at either side of these creeping zones, you can go and look at the time series when it's released and actually look for any changes that might be happening through time. This looks fairly constant creep across here, but there will be some time varying behaviour as well in some of the areas. As I mentioned before, we need to correct for the earthquakes, but what we don't do is correct for any post-seismic deformation. The after slip that you get and the post-seismic relaxation that might be deeper, lower crustal, we don't account for that because we can't properly model it. So that stays in our strain rate field. We've removed the large co-seismic, but it still really pops out in the velocities because you get the velocity gradients and therefore the strain localizations for some of these earthquakes. And in fact, an earthquake 30 years ago, the Manu earthquake still really flashes out there as a large strain rate across it. And in fact, a recently submitted publication by a colleague has probably shown that we can detect this post-seismic over 100 years ago from an earthquake 100 years old, and perhaps we've got examples even older of post-seismic deformation. So it's very, pervasive. It persists through the time series. So we have to decide how we account for this in the strain rate field. Because it's there, we're measuring it. It's an important thing to account for, but it does, for some of these earthquakes, persist for a very long time. And here's an example also of the time series then for a relatively small normal faulting earthquake in the Tibetan plateau, where you can see the initial rapid after slip related, probably post-seismic, and then it decays through time. So we've got those time histories as well for those areas. So what we want to sort of understand at the large scale was, how does the seismicity correlate with the strain rates? Do they map one-to-one? So here's our strain rate map. And then here's the compilation from the ISC GEM catalogue for the last 100 or so years of magnitude 5 plus shallow earthquakes above magnitude 5 that are shallow enough, less than 35 kilometres. And you can see that in areas of high strain, you get lots of earthquakes, but in areas of some low strain or distributed strain, you also do. But in relatively aseismic areas, they're relatively low strain as well. But there's not an easy one-to-one correlation between them, but that would need a bit more work to sort of map that a bit better. Similarly, for where the faults are, this is our maximum shear strain rate, so largely associated with strike slips. If we overlay the GEM fault map database, it lines up with really large, well-known, fast-slipping 10 millimetre per year faults, 30 millimetre per year faults. But there are large numbers of faults that are in really quite low straining areas. So that's the take-home message, that you still get these active faults, even with relatively low strain. So we still want to measure these low strain rates. When we're down at the 25 nanostrain, we're getting near the noise, particularly in areas that are incoherent. But we want to be able to measure low strain rates because they still lead to active faulting and probably seismicity in those areas too. So the individual study areas that have been focused on by Sentinel-1, I showed you Turkey before, but we've had a number of studies across the Iran Caucasus as well, as the Tian Shan, and a large number across the Tibetan plateau. So if we look at Turkey, these are the HB results we've just generated, zoomed in those different components I showed you from the velocities and strain rates. And if we look at what we had before, I'm sorry it's on a different color scale, it makes it harder to compare, but you can see we've started to really tighten up how well we can resolve it with twice as much data. So more data makes better results, as you expect. We're getting lower strain rates nearer zero where we are. The higher strain rates are more laterally continuous than they were in the previous study. And when we start to look at things like the dilatation, it's a bit more consistent than it was in the past. It was very blotchy because all the frames weren't referencing well together. That's much improved now, and you get really quite a clean result in Eastern Anatolia, for instance. You clearly get the positive dilatation in Western Anatolia. So we're improving it by expanding the time series, and it will continue to increase in time, but the noise will not massively change in the future. We've done most of the gains that I think we can get through having 10 years of data. Having 20 years of data obviously won't improve it by a factor of 2. If we look at those profiles, you can see the strong concentrations across the North Anatolian fault here and the East Anatolian fault with those spikes in strain rates. And you see across Anatolia, our noise floor. So this line here showing the max shear is very near zero. So in good areas, we really are getting down to very little strain. So these are nice, believable results here. Not much noise in those low strain rates on this profile here. There's a number of studies in the Iran Caucasus as well. So here's our result from the HB, showing really quite distributed deformation. But Andrew Watson and Nick Dodds showed much more localized distribution in individual studies over individual faults, as well as some more recent studies across the Caucasus. But you can see not quite as much strain concentration here, really quite distributed across the Zagros here. But we've got a nice large bit of north-south shear here, which I'll come back to a bit at the end. For the Tian Shan as well, we've got our overall results here showing really quite broad, low-level distributed deformation associated with this convergence, the dilatation being negative, this compressive area. Lot of vertical velocities that I'll come back to related to substance, but we get quite a large gradient in the eastward component. So that is just been recently accepted in Nature Communications. Chiu has delved into this and has suggested that there's a nascent shear zone at depth running right beneath this mountain range, something a bit controversial, but something that we're seeing in those velocities there. It might be the onward propagation of, say, the Shaman fault zone from the Indian collision right through the Tian Shan here. And then at the Pamirs, this is really quite a large signal that we're getting across the Pamirs. You see in the eastward component that the maximum shear strain rate is really popping out. This area is really quite a strong concentration in the velocities that we get here. Huge amount of deformation right at that Pamir front. And if we look at the long wavelength, this is an area that I'm speculatively consider maybe the vertical velocity might have something in it. You can barely see the misfits to the GNSS there, they're coloured the same. But there is some evidence that there might be some long wavelength uplift in this region, which would be interesting to delve into further. Then Eastern Tibet has been a large focus of Jin's work. He's published a great number of papers on this, trying to understand both the kinematics and the dynamics that's driving this area. But here's the HB version of the results, where we see the loci of those strain concentrations and the Janjarier fault creeping segment bits. But we got the strain concentrations here across all those faults there. So there's a large number of studies with great findings for there. And similarly for the northern Tibet, we've published a couple of studies on this, but the Altintar fault really has this extensive strain concentration on it from the left lateral sense of motion across it, as well as the Manu fault and the Kunlun fault. So these are all in there too, and there's working review on that. So just to finish on that large component, what does the vertical deformation say? This one largely contains big signals at short wavelengths. But one of the reasons we're a bit skeptical about it in parts of the Tibetan Plateau is due to the permafrost here. This is a near surface effect in the soil due to thawing and freezing that means that we might get apparent vertical motion on a seasonal scale and then a long-term apparent substance that we get across here. So we might be looking for a long-term uplift maybe in this area or certainly at the margins, but it's certainly overprinted by a near surface effect here. So that's something to watch out for here, Tian Shan, other places that have this near surface effect where it's cold. And we can see that if we try and look at the vertical, the noise is quite large across these permafrost regions, making it really quite hard to measure. Vertical deformation is always going to be a much smaller fraction of the horizontal deformation in this area. What is big for the vertical is water-related substance. So here's outside Beijing with many tens to hundreds of millimeters per year of subsidence associated with water extraction over many hundreds of kilometers, and that we can easily see in the data here. And that's replicated in parts of the Tian Shan here near the Jungar Basin. That's seeing a similar effect over hundreds of kilometers of subsidence, as well as in the Kuru Basin in central Turkey. And across huge parts of Iran, we see large numbers of basins subsiding there from the water extraction. And again, you can go and delve into the time series, a couple of relative points here. Of course, that looking at the time history of that decaying and whether there's time varying behavior in that substance ring. And in fact, Jess, for a PhD, did a compilation of over 100 basins subsiding in Iran. And we've got that data set on our COMET substance portal that you can interrogate. So it gives you the average velocity here in the center and the time series history, whether it's filtered or unfiltered, for each of these 100 and so basins. And you can download the data as well at high resolution. So then just to finish, what's the outlook for this field and where are we going next? Well, one of the aspects that is the ongoing sort of processing. So Sami Esfahani manages the processing chain, and Milan develops all the software for it to be able to incorporate improvements into the processing chain for this. It's also through the COMET LIX system portal and is being developed, the LIXAR processing and LIXBAS through the GitHubs here. So they're making huge efforts in keeping this up to date, dealing with the big data volume challenges to be able to do it at this scale. Similarly, there's improvements in what we do with the filtering. We did merely doing filtering before, but Feng Lian Chang has been working on a technique to better account for any contrast in velocity across these velocities, which makes great improvements in the Pamirs. If you do Gaussian, you get very blurry picture. Median seems to smooth stuff out, but the bilateral preserves sharp gradients and sharp edges that much improves it when it's localized. So it'd be good for creeping zones and strain concentrations along here. So that's currently available as a preprint for improving velocities. Then there's also work on burst overlap interferometry. Here's an example from Iran, from Parwan Paremthong, who is looking at the north-south motion here. Now, InSAR, traditional InSAR is completely blind, or almost blind to that north-south component, as I said earlier. But if you look at the long-track burst overlaps, you can get displacements a bit noisier than with line of sight deformation, but it gives you that third component that we want for many of the faults in the area. And Mohammed's been doing the same with both burst overlap and the subswath in eastern Turkey, being able to capture both the earthquakes and hopefully the long-term and seismics, being able to do this better and better, incorporating that important north-south component. So this has been part of quite a long journey from the early ERS ENVISAT data where we could look at individual faults through to the constellations, the systematic data that Sentinel has been able to provide us, and the recent launch and data that's been provided by Sentinel-1D has been able to enable us with the open access data to do this at huge scale. But in the future, we can look to be able to incorporate both different bands, L band here from Roselle, from ESA, and also Harmony to try and again get at those north-south components and DMs and things like that. And potentially, like we're looking at the next generation missions of Sentinel-1 continuing this on an operational basis. That's going to provide huge data streams for this sort of work. And tentatively, one of the 4 missions for Earth Explorer 12 is a SAR, geostationary SAR, Hydroterra ++++, that it could potentially be selected for this mission as well. So the future mission capability is looking good. NISAR is going to be the step change now, launched last year, going to be providing large volumes of data soon from July, hopefully. It's going to make quite a big difference. The L band is going to enable us to cover parts of the Alpine Himalayan Belt we weren't able to. Harmony has been selected. Its anticipated launch has just been shifted because Bezos has been nicking some of the rockets, so they have to launch Amazon stuff. So it's been probably shunted a bit to 2030, but that will provide again a different component for us. And then the next generation is going to move this now to sort of beyond the science to really quite a continuity, continuous sort of ability to resolve this with these kinds of methodologies. And what we're trying to do next with the project that Andy Hooper's leading is to look at the bit that we're missing. Now, the Alpine Himalayan orogeny is all about north-south motion, and it's one thing the InSAR is not very good at measuring. So what we want to be able to measure are these north-south orientated strike-slip zones, so the Dead Sea Fault, Eastern Iran that I showed you with Paran's work, the Shaman Fault zone with those large creeping segments, and the Sagan Fault that just had that recent major earthquake on. We're missing those in this sort of data. They look low, they're not low strains, they're going to be high strains, and it's our lack of ability to resolve them in our observations. So we want to be able to get at these fault zones, and with a recently funded project, we're going to be able to do that. So if we take a hypothetical strain rate across instead of an east-west, a north-south orientated fault now, with our traditional Sentinel-1, we have 2 look directions. It's right-looking, so we right look on ascending, right look on descending. We can't retrieve the strain rate at all. The shear doesn't appear in that. But with the diversity of look directions with NISAR looking in the left direction, we get more information than we did before, and now we can resolve that much better. So with now 4 look directions that have some diversity, they're still not perfectly north-south, but they are looking in opposite directions to each other. We can resolve that much better, not perfectly, but much, much better, hopefully. So that's what we will do in the future. So in conclusion then, last slide here, the findings from Sentinel-1 has enabled us to generate really quite a detailed velocity field over a trans-continental scale. We've been able to do this at a big picture. The horizontal motions, this is the eastward velocity, the horizontal motions are dominated by the tectonics. The vertical is all about aquifer-driven substance. The strain is localized on the major known faults we already know about. Diffuse deformation happens everywhere else off these North Anatolian faults, East Anatolian faults, the large strike-slip faults of Tibet. Everywhere else is really quite diffuse. Doesn't mean it's absent. Even areas that are 20 nanostrain per year have active faults, they have seismicity. We want to be getting down to the sub 10 nanostrain per year if we can. And the conclusion from those faults that do pop out, I feel, is that the loci of the current strain are the scars of old earthquakes. So we're not accounting for the post-seismic, they're in there. It's not maybe semantics, but is it the interseismic strain, or is it just a remnant scar of the post-seismic heightened deformation you get after an earthquake? Because it's not just 10 years or 30 years, it's over 100 years that we see the strain associated with some of these largest earthquakes persisting in these velocity fields. So they're still there in there. So there's been a number of challenges to be able to do this. It's really hard to measure the long wavelength deformation. This referencing still isn't perfect at that. And to get to slow strain rates below 20 nanostrain or 10 in good coherent areas. The north-south has come entirely from the GNSS. So where we don't have GNSS, it's not going to be any good. Even if we've got some long wavelength constraint, it won't be any good. So in the center here, it's not very well constrained around Afghanistan. The vertical rates are largely unreliable. Short wavelength, rapid substance, yes, very reliable. Long wavelength, if you want to interpret them as tectonic, other than the Himalaya uplift, the Chilean Shan, maybe the Tian Shan and Pamirs, I believe maybe with a bit more work. Other areas they can be overinterpreted. They're going to have impacts of, water extraction at large scale, drying out, maybe something else, but we've not got them referenced well enough to be believable. But hopefully a bit more, these things can be mitigated to north-south with future missions, vertical rates, maybe with better timing of data. And then systematic coverage in areas of dense vegetation. As we move southeast, you can see the eastern syntaxis here is completely absent. That's going to be impossible with this kind of approach. We did distributed gas scatterers, SBAS approach, not persistent scatterers. It's not going to be possible in these areas of vegetation really to do much with it. And then that's where L-band's really going to come in with InSAR to make that much more tractable. So there's some hope that we can address these challenges with some of those upcoming missions. And there's also hope that we can improve some of the strain rates, but this is sort of the landmark data set that we have at this sort of resolution for this whole Alpine Himalayan Belt. So thanks for listening. I hope that wasn't too bad, but yeah, thanks, Jim.
And for some quick questions, do you have access to the Q&A box from your side or
me?
Read questions from you.
Yes. Well, that's a lot of questions. Right. So the questions are, this is Jobal from Ethiopia. What if I want to work for more than one neighbouring scenes? So the data we have, we've referenced it all together. So if you take the reference data sets, then you can work on the neighbouring scenes and they will be fairly consistent, but check when they overlap, you'll get some apparent discontinuities, particularly at the 1 kilometre resolution, the non-smooth version. But yeah, you can use the adjacent scenes with a bit of caution when you do that. You may need to do some smoothing or adjustment, but they're largely consistent. As the interferogram generation in software is you require a lot of computing. Can you use COMET's interferograms for time series analysis? Yes. So that's the idea. It's quite a computational effort. It needs high performance computing to generate all the interferograms. So we made them openly available on that portal. So I provided a link for that. So yeah, you can download the interferograms, use LixBAS to do the time series, which is slightly less computationally expensive if you don't do it at high resolution. So yes, you can do that. How do you validate it in areas with no ground stations like GNSS? So that's a good question. It's very hard to validate. It really is. If we've not got an independent data set or semi-independent data set, it's really quite hard to do that. We don't really have a good measure of that. It's basically the gut feeling of how does it look. It's got to be consistent over long wavelengths, so you can't have huge velocity changes. But as I said, the vertical, you can't believe where there is no GNSS, and we don't have a good constraint on. Is there any attempt of using deep learning and AI for deformation monitoring? Not by us in this study. It's done for some of the volcanic deformation. So if you look at the COMET volcano portal, there is some of that by Pui. She's done some works on a sort of alert for that. And also Matt Gaddis previously did some work. So some of us have, and you'll be able to find out about that on the system, but we've not done it here. We're not doing a sort of real-time analysis. We've not trained it on any of this. There's not large data sets for doing it. And we've not really done it on the earthquake side. Brilliant. Thanks for those questions. Another one. So there's just comments. Okay. Any other questions? Anything from here? Yes, Benji.
How big are the nanostrain? Like the nanostrain, you're talking about things being a couple of nanostrain or whatever that you're measuring.
Yes.
Nanostrain. Like how, if you can visualize that with like a rubber band, for example, like how big you're actually measuring.
Yeah, so that example at the beginning, that 10 millimeters, if you had a rubber band and you stretched it over 100 kilometers by 10 millimeters, that's your 100 nanostrain. So you got, if it moves that much across 100 kilometers, that's what, that we can easily measure. Trying to do 1 millimeter change across 100 kilometers, we can measure when the coherence is good. Only when it's good. Now that we've got long enough time series, you can do a 1 millimeter per year change over 100 kilometers. Yeah, if it's horizontal shear, yes, that's doable. getting 0.1 with millimeters per year over that distance, I don't think is realizable even with another 10 years of data. I think it would be nice, but just the basics, root n signal to noise ratio, doubling the data set doesn't get you down an order of magnitude. You do not do that. It will improve a bit, and there'll be different techniques and different filtering techniques that can be done to make things better. But the inherent sort of ability to measure that velocity well from pixel to pixel is challenging, because the short wavelength noise is quite large. We could do it try and run this instead of 1 kilometre at 100 meters to improve the apparent resolution, but the strain rate resolution wouldn't be better because the noise will still give you large apparent strain gradients that just aren't real. You want to, for continental things, you got to think over the 100 kilometre wavelength, unless you're looking at creeping zones, which are large magnitude things that you could look over a kilometre for. Yeah. That's fine.
You mentioned all the way at the end to get the north-south deformation. You had this concept of using InSAR alongside Sentinel. I was wondering if there's any like precedent of previous missions being combined, like multi-mission for like getting all three deformation components. So not necessarily time series, just conceptually, like how well does that work if you have different wavelengths?
Yes, yeah, well, different is the diversity of geometry. So yeah, people have shown that theoretically in the dilution of precision that you'd get. There's also the RadarSat constellation mission has the diversity of some of the RadarSat ones. So somebody must have done that.
Sorry, I mean in the sense of like having to combine different wavelengths. I understand the point that if you have different geometries, that will help you decompose, but like how much of a challenge is it? Like how much different signals are you looking at when you've got different wavelengths? That pose a lot of challenges.
Yes, I think we probably haven't thought about it enough that it will in some of those, but bare rock areas, the penetration into the bare soil will be different.
Yeah.
I don't think it may impact it little. In vegetated areas, it definitely will. We'll be measuring different height of scatterers probably. So yes, I think they may be not consistently measuring the same scatterer. Yeah. So I think that will be a challenge of applying that method in some of the areas. Yeah.
Yeah, so that's not something that's already been in the past a topic of study.
I bet someone's done it. I've not thoroughly researched enough to know, but I could guess. I bet it's a problem. Yeah. Definitely.
There are a few more questions online as well, just as a heads up.
Sorry,
Sorry,
guys. Where are we now? Sorry, I can't see those. Can someone help me see them? Oh, the new posts are up. Thank you very much for the presentation. How much differently did you process mountain areas than flat areas within SAR? And how did you merge different swaths? So yes, it's pretty consistent in some of the processing chain in generating the interferograms. You use the DMs to unwrap, so they perform differently in flat areas versus mountains, but the approach is generally the same. The gas cost correction would be doing more work in mountain areas, but won't always perform so well with the heights. So it does vary a bit. And then when we come to some of the time series analysis, we did tweak some of the parameters frame by frame, and that will correlate with land cover a bit, what we had to do differently in the Himalayas, which really struggled, to be honest, to get some of it because it's so steep. It does vary a bit. And then merging the different swaths. So along track, we merge them and try and minimize the difference. But VelMap is the bit of software that's basically trying to merge those line of sights together. So that bit of the talk where I'm talking about VelMap is how you're doing that. So the swaths side by side in line of sight will always have some difference because they've got a difference in the viewing geometry. But they should be referenced along track quite well. But swath to swath, side to side, they'll be a bit different. When you solve for the velocities on the node, it's accounting for that difference in velocity. But if you look at the reference line of sight velocities, there'll still be some difference. So you need to decide which of the data products you're going to pull to work with. Afghanistan question. Northeastern regions such as the Hindu Kush and parts of the Pamir experience frequent earthquakes almost every day, along with significant seismic activity at shallow to deep depths. In your search, compared with other parts of the Himalayan belt, this Northeast African region appears to exhibit relatively low maximum shear strains. However, the sparse distribution of seismic stations GPS data may partly influence the observation. My question is, are there additional tectonic factors that may also contribute comparatively low surface shear strain rates despite the high level of seismicity. Yeah, I mean, Afghanistan and the Herat fault and the earthquakes that happened there, and which were relatively big, 6 and a bit, and the general seismicity is a bit of a quandary. But if you look at the overall velocities, it really is a bit like those American freeways, I always think, with the water buckets at the off-ramp. It's sort of a buttress that India and Arabia go around, and it's not moving north much. It is relatively aseismic, but it's only relative. It's obviously still got a lot of seismicity that can be quite deadly, but relative to the bits either side of it that are taking out most of that north-south shear. Yeah, I don't understand that region as well as you do, and it's weird that it's really quite low. Now, as you say, we are insensitive to that north-south, and that new project accounting for that north-south should better resolve some of it, but it looks a lot lower straining. But as I say, below 10 nanostrain per year doesn't mean there's no seismicity, and that's the challenge of being able to ever convert any of this to seismic hazard when it's that low straining. Low straining continental interiors are going to be very hard to really characterize over a 10,000 year time scale, because that return time bit is quite long. You just would have no idea about I think the earthquake recurrence for that. From the GNSS results presented, I noted that there is non-negligible horizontal deformation along the coast of China. If I were to ignore the horizontal component and simply project the lines of that deformation onto the vertical, might that introduce potentially large errors? Was there the horizontal deformation on East China? Was that was it horizontal deformation or horizontal motion? Because it depends whether there's if the velocity is all pointing the same, it's moving relative to a reference frame, but it's not necessarily deforming if they're all translating as a coherent mass. So I'm not quite sure with Eastern China which bit that is along the coast, I assume. Yeah, it would do if it was deformation that you assumed to be horizontal and then put into with vertical and then put into the horizontal. I think it would have some errors, but I'm not sure that's what we're seeing. But sorry, I can't really understand that question. And I've answered that one. So I think that's all of them, isn't it? Yeah.
So
oh, Benji can't stop.
Oh, Benji's got, I can see in the room, Benji's got another question. We'll probably have one more, and then if there's no other questions in the room, we'll tie it up. Again, thank you all, but yeah, Benji.
So you get some north-south constraint in areas where there isn't much GNSS. Did you ever consider using some of the burst overlap, or is the noise too much and the coverage not dense enough to actually provide much value?
Basically, it's quite hard work, isn't it? And it's only recently being developed. Like it's quite frontier stuff. The line of sight InSAR is much, we started this a decade ago. It's much more established approach. It was just a bigger, different scale. The burst overlap interferometry was always a bit of a challenge to be able to get going, because you've got to sort of average it more, understand it more, and it's still coming on leaps and bounds what can be done. So it's what you would want to include next, but to process at this scale, we needed to have made choices years ago about retaining some of the intermediate data products to do it. That was the difficulty. If we'd kept more, if we had bigger disks, these are disks that are, half a petabyte, and we're always filling them up. You need many petabytes to do this, or you need to throw away data all the time, and we couldn't keep everything. So now whenever we do an area, the idea is to retain the kind of products that we need to use to do that kind of work, and to try and cleverly keep them. But yes, it would, if we were to do a version 2, it would be a challenge, but you would introduce that, I think, would be the aim. Okay,
I think we'll have to stop there. Thanks again, thanks John, and thanks everyone for joining us today. Our next webinar is scheduled for June the 19th. So we look forward to seeing you again. Thank you. Thanks everyone.
Thank you, everyone. See you later.